Good evening. Today we are with the topic that is in structural analysis influence line diagram. Is a actually graphical analysis we can say for determinate and indeterminate beams. Here in this video we are going to plot the influence line diagram for simply supported beams and cantilever beams, and we are going to solve the problems on this. Now, what is influence line diagram? Actually, this is the simple concept if we will talk about influence line. So, influence line diagram is the graphical representation for any stress element. Now, stress element, we can say we have reaction, shear force, bending moment, torsional moment, etc. So, we have this stress element and we are going to find the values at different point, and then we are going to connect all these points, and therefore we are saying this is a graphical representation. But this graphical representation we are going to be when unit load is moving throughout the span. So when we will go for influence line diagram, we have to remove all the loads and then we have to move unit load throughout the point, and then we have to plot the values, and then we have to plot the influence line. So now what is benefit of this? So once you have plotted influence line diagram, then you can change the loading on the beam and just multiply load into ordinate, and you will get reactions, you will get shear force at any point, you will get bending moment at any point. So all calculations you need not require to go for. So influence line diagram for a particular beam, that remains same, that is not going to change as per your loading. So influence line diagram is independent of the external loads acting on the beam. Now, first we will go for simply supported beams, and in that we have first influence line diagram for reactions. So now draw influence line diagram for reactions at supports for beam A, B as shown in figure. Means we have to plot influence line diagram for beam A, B, and that for reactions at A and B. Now, as we have seen, when we have to go for influence line diagram, we have to remove all external loads and we have to apply unit load, and that unit load should be moving unit load throughout the span. Now let us, we have unit load, let us consider at a distance x, and then we are going to find out the values of reactions at A and B, and x value varies from A to B. That is, at A we have 0 and at B we have L. Now you can see we have this unit load, we have to move throughout this span, value of x that varies. Now, how we will go for this? So simple, that is equilibrium equations. We will find value of RA, we will find value of RB in terms of x, and then we will substitute value of x at different points. And by that, we are going to plot these all values of RA, we are going to plot all values of RB, and then we will connect these values. That will give us influence line for reactions. So now we have this equilibrium equation, moment about A0. So we have, this will be moment about A0. And then from this moment about A0, we are going to get this value that is equal to minus RB into L plus 1 into X, and that is equal to 0. And that will give me value of RB equal to X by L. And then we will apply Fy equal to 0, which will give me value of RB. And that value of RB, we are going to get it as 1 minus RB, and that will be 1 minus X by L. So we can say it L minus X by L. Now we will put this unit load, and knowing RB, X by L, and RA, 1 minus X by L. Now you can see we have unit load at A. So when unit load is at A, we have X equal to 0. So if I will put R in RB X0, then I will get RA1, we will get RB value. As RB is 1, so if we will substitute, X is 0. So if I will put value of X0 in this equation, then I will get value of RB that is equal to 0. Once I know value of RB, I will substitute in this equation, or you can put X in this equation, you will get value of RA1. So we have 1, we have 0. To total, we have always 1. So whatever number of reactions you have, if we have compound beam, then we have number of reactions more, but total is always 1. Now we have second, we will put value that is at L by 4 from A. So if I will put L by 4, then RB we will get it as 1 by 4. And RA, if we will put 1 by 4, then RA we will get as 3 by 4. And total we are going to get it as 1. Now we will put value that is at L by 2 from left hand, that is from A. And in that case, our value of X is L by 2. And from this, we will get value of RB as 1 by 2. If we will substitute RB 1 by 2, then we are going to get value of RA also 1 by 2. And total, we are going to get it as 1. Now, then we will go for 3/4 L from A, and then we will determine value of RB 3 by 4, then RA 1 by 4, and again total we are going to get it as 1. And then last we have that is unit load at B. So when we will put unit load at B, X is L, RB we will get 1. So if RB 1, then RA automatically we will get it as 0. So knowing all these values, we are going to plot this. So we will plot it first, that is for RA, RB. So we have value of RB, you can see at L by 4, we have 1 by 4. At L by 2, we have 1 by 2. Then at 3 by 4L, we have 3 by 4. And at L, we have 1. So we have plotted these values and then we have connected. That will give me ILD for RB. Similarly, I will plot ILD for RA. I will plot at A, we have value as 1. At L by 4, we have 3 by 4. At L by 2, 1 by 2. Likewise, we will plot it. You can see it. And by plotting this value, we are going to connect all these values. And by connecting these values, we are going to get that is value ILD for RA. So we have to plot ILD for RA in this fashion. This is always a triangle. Then we have ILD for shear force. Let us, we will consider a point where we have to find out ILD shear force. So let we have distance A at which we are interested to find out shear force. Now in this we will have this unit load. First between A to C we have one equation and C to B we have another equation. So we are going to get two equations to plot shear force, and then we are going to determine the values, and then we will plot these values, connect these values, gives me ILD for shear force at C. Now you can see first we will consider that my ILD, that my unit load is between A to C. So when unit load is between A to C, then we will consider two parts. So what will be my left part? So you can see my left part is in this fashion. Then what will be shear force? That is unbalanced force on left of C. So we have RA upward, 1 downward. So I will get it as RA minus 1. If I will consider right part, that is CB, then you can have right part CB. We do not have any load on right part. So we have RB, but RB is upward and that is in right part. So my shear force is minus RB. So when my unit load is between A to C, I can consider shear force as RA minus 1 at C, or I can consider shear force at C as minus RB. Now if my unit load is beyond C, that is between C to B, then what will be my equations? So you can see, so we have now unit load that is between C to D. So now if it is between C to D, then we have this will be left part in which we do not have any load, we have only RA. RA upward, left side we have plus. So my value of shear force at C, we are going to get it as RA. But if I will consider right part, then you can see in right part we have unit load now, and one is downward, so plus RB upward minus, and my shear force becomes 1 minus RB. Now out of these four, we have to consider two, one from A to C, another from C to B. Now you can see which we have to consider. So now whichever becomes easy for us, that we will consider. Now we will consider in A to C, that is minus RB. And in C to B, we will consider RA. Well, we are considering likewise because we know ILD for RA, we know ILD for RB. So between A to C, we will consider ILD of RB with minus sign. And between C to B, we will consider ILD of RA with plus sign or as it is. So you can see here. So I will plot ILD for RA. I will plot ILD for RB. So we have this, whatever we have this ILD is for RB. We have plotted with minus sign. And this is ILD for RA. We have plotted it to positive side. And now we can see this. Between A to C, I have to consider RB. So RB between A to C, then you can see value is 1 by 4 that we know because it is at L by 4. Now, if you will go to C to B, then we have to consider that is ILD of RA, so we have considered ILD of RA, and this will be 3/4 because it is the 3/4 from B, and so we have this value. Always keep in mind where you are going to find out shear force to total ordinate. So I can say this total ordinate, this value should be always 1. So you can see, so I have this as ILD for shear force at C. So this is ILD for RA, this is ILD for RB. Now then we have ILD for bending moment. Now this is simple one. So in this we are again interested with point A, and here we are interested to find out bending moment, ILD for bending moment. Now where you have to find out bending moment, ILD for bending moment, you have to put a unit load at that point. Now we are interested at C, that is at a distance A from A, and therefore we have to put unit load at this. Now if I will put a unit load at C, then I will find values of RA, I will find value of RB. So RB I will get as A by L, and RA if you will find, then RA you will get it as L minus A by L. So we will write these values of the reactions at this. So RA L minus A by L, RB A by L. And now we will take moment about point C. You can take moment from A also, you can take moment from B. So by any side, if you will take the moment values, you are going to get it as same, and that is L minus A upon L into A. Or if you will take from this side, then this distance is L minus A. So you can take from both ends. So values you are going to get at C, these are same, and then you are going to get this value, that is ordinate of the ILD for bending moment at C, and that is value is A into L minus A upon L. So this is my ordinate for influence line diagram for bending moment at C. So these are the bending influence line diagram for simply supported beams. Now we will go for influence line diagram for cantilever beams, and in that we are with reaction, shear force, and bending moment. Now let us we are interested to plot influence line diagram for RA, MA, and shear force at 3 meter from A, that is at point C. Now you can see this, we will have to go for unit load, and then we have to plot this. So now in this, if we will go for ILD for reaction at A, now here we do not have any other reaction, so my value of RA is always equal to 1. So my ILD for reaction at A is simply value 1 throughout. So it will have a rectangle and having value 1 throughout. So this is my ILD for RA, because RA is going to take unit load always where your unit load is moving from A to B. Now we can have this for shear force at C. So again we have same concept. So we have to consider unit load between A to C first, and then write down the values for shear force at C from left from right, and then unit load from C to B, and then again write down equation for A to C and C to B, and then whichever becomes easy, that we will consider to plot influence line diagram at C. And then you can see over here, so unit load is between A to C. So what we will get it, so if A to C we have, then we have that is RA minus 1. MA is there, but we are with summation Fy, not 0. Summation Fy equal to shear force, and therefore we have RA minus 1. And if we will go in right part, then right part we have equal to 0. If we will plot the diagrams over here, then I will plot the diagram. Then we have this diagram. I have over here RA, and then we have value of 1 somewhere between A to C. So we have this will be value 1. So MA is there, but our MA will not come in the equation of force. So we have MA over here. Now if we will go to CB portion, then we have CB portion, simply nothing is there. So this is CB. And therefore I will get shear force here, that is equal to 0. Now if we will go to unit load between C to B, then what will happen? Left part. So now you can have C to B. So in C to B, if I will go over there, then we have in this fashion. Now unit load is in right part. So here we have only reaction RA, and then here we have MA. So MA will not be there in the equation of force. So we have only that will be RA, and I will get it as shear force at C equal to RA. You can see over here. And then if we will consider right part, what will be in right part? So shear force equal to 1. And then if I will plot it, then we are in this fashion CB. And then unit load will be here. And right part we are considering downward, we have plus. And we have, this will be my equations. Now whichever we have to consider, that is our choice. From A to C, we have to consider 1. From C to B, we have to consider 1. So we know ILD for RA. And then by using this, you can plot ILD for shear force at C. Then you can see this. If I will, now which we have to consider. So now if I will consider between A to C, this portion, so my value is 0. So you can see from A to C, my value is 0. And then, so I will mention, so we are going to consider this equation, and then we are going to consider this equation. Then I in between C to B, what is my value? 1. So I have plotted this value. So here somewhere you have A, here you have this as C, and here you have B. Now, if you will consider this also, then you have to consider this ILD for RA, that is between C to B, and you will again get it as 1 only. So that is your choice, which equations you have to use. And then we have for bending moment at A, and in bending moment at A, we have to write down one equation only because everything is on right of A. So we have equation that is, this will be FBD of B may be. And then if you will write equation for this, then my equation will be bending moment about A0. So 1 into x minus ma. We are taking moment at A, so RA will not be participate in this one. And then I have ma equal to x. So x means that is linear. So value at A of x is 0 and value at B of x is 6. And then we will get it as a linear line with ordinate at 6 at B and 0 at A. So this is my ILD for bending moment at A. So these ILDs we have to plot in this fashion, and once we are in position to plot ILD, then problem solving by using ILD is very easy. Now we have two problems over here. First we have consider a beam AB, and we are interested to find out shear force at C and bending moment at A from left support, that is at C only. So now we will go for this. At A, I will mention it as again at C. Or at, you can write 5 meters from A. So now we will go for this. So we know now overhang is there between E to B. So whenever you will go for ILD, you do not consider overhang. First, you plot ILD between simply supported points, that is AE, and that we know. Whenever we'll go for ILD, you have value of ordinate of at that reaction is 1, and at all other reactions we have 0. Now here we have two reactions only. So at A we have value 1, at E we have value 0, and then we have to extend it. That is, we have linear always. Your line that is linear always for ILD, and then you can see this. So we can go likewise. So you can see, if I will consider a pen and if I will draw an influence line diagram for this, so if I will take it up, then we are going to be 1 at A and we are 0 at B. Now, if I have to plot at B, then I will take B up. So B, we have 1 at B, 0 at A. If we have in between, then you can see over here. So if we have to go in between, reaction is here, we are overhanging. So you can see beyond B, we are going to get it as negative. Now, if I am going to plot at B, we are overhanging, then you can see you are going to get ordinate at B greater than 1. So we have to plot in this fashion. So here we are in the same way. So we have this value that is 12.5 by 12.5 because this value is always 1. So whenever you are going to plot it, so at that reaction we have 1. And then accordingly we have to plot other values. So you can see my distance. We have to measure from 0 height. So from this, from E, I have this distance as 7.5. So 7.5 upon 12. Similar triangle we are going to use over here. So here we have 5 by 12.5. And if we will go at B, then we have 2.5 by 12.5. So this is my ILD for reaction at A. Now, if I will go for ILD for reaction at B, then we have to consider 1 at E, 0 at A. And then we have to extend that linear line. And then you can see we have this linear line. So value at E, we have 12.5. So 12.5 by 15, and here my value that is equal to 15 by 12.5. So my distance is same. So we have this ordinate, which is 15 by 12.5. So this value is definitely greater than 1. So we are going to be distance, we have to measure from this point. And then we have to go for similar triangles, and then we have to find out value that is at point D we have 7.5 upon 12.5, and then at at D and at C we have 5 upon 12.5. So we have, this will be ILD for, this is ILD for RA, and then below we have ILD for RB. Now we will find reactions using this. So we have to just multiply load into ordinate. So now if we have concentrated load, then we will multiply it by ordinate. But if we have UDL, then we have to multiply it by area. So if I have to find RA, then we have to multiply with this area. And if we are going to be with this, then we have to multiply that 10, and this portion we have to consider. So whenever you have UDL, you have to take area under it. And whenever you have concentrated load, you have to take ordinate below it. And then you can have these values. And we have RA, so we have 10. So if load is downward, ordinate is upward, then we have plus value. Because if this is opposite, we have minus on left side. So when it goes on right side, it becomes plus. So we have 10 into area of this. So 1 half 12.5 by 12.5 plus 7.5 by 12. So we are going to get this first, which is 10 into this value. Then we have plus 40 into this value, 5 by 12.5. That is under 40 kilonewton load. And then we have plus 16 into 1 by 2 minus 2.5 upon 12.5. Now you have choice. You can take this value as minus, and then you can have this value as plus. That is when they are in opposite. Then when they are in same direction, we have positive. When they are in opposite direction, we have negative. And we will get this value as 52 kilonewtons. Now you can go for RB, and in this case we have RB that is equal to, then you can see this is 1 half. Now we have triangle, so directly we have 1 half base into height. So 10 into 1 by 2, 5 by 12.5 into 5 this distance. Then 40, 7.5 upon 12.5, and then we have to consider this area. Now these are in opposite direction, so we have to consider it as plus. So we have taken this as 16 into this one, that is half 12.5 upon 12.5 plus 15 upon 12.5 into this distance 2.5, which will be 78 kilonewton. Then you add these two, then RA plus RB equal to total load. So total load you can see 10 into 5, 50 plus 40, 90, and plus 16 into 2.5. So 32 plus 8, 40. So 50 plus 40 plus 40, so it becomes 90, 130, and 78 plus 52, that is 80 plus 50, 130 kilonewton. That means our values are correct. Now you can go for shear force at C. So just already we have seen, we will draw ILD for RA, we will draw ILD for RB, and then we know we have to consider between A to C, we are going to consider that is ILD for RB. So now here we have RE. So RE we have to consider between A to C. So this portion we have to consider when we will talk about A to C. And then for remaining, we have to go for this portion. Total. Then you can see this. So this is now not B. So we have, this will be for ILD for RE. And then you can see this. And then we have portion that will be as it is, that is ILD for RA. And then we have to just multiply. We have seen this value. So this value we have 5 upon 12.5. So you can see there. So both are in the same direction. So my value should be negative. Then you can have ordinate negative, or you can take value negative. So this is 5, 12.5. And here we know this value we have 7.5 by 12. Now you can see ordinate, already I have mentioned this ordinate should be always 1. And you can see total ordinate, not algebraic sum I am saying total ordinate. We are not going to, that is magnitude we are going to consider, and that we are going to get it as 1. And then we have to multiply RA minus 10 into this area, 1 half base into height, plus 40 into this ordinate. And we have this ordinate that is 5 upon 12.5. So that is taken plus, because both are in opposite direction. And then we have this area that is again in the same direction, so minus. So minus 16 into this area. So we know this value we have 2.5 by 12. And likewise, we are going to get value of shear force, and that value we are going to get it as 2 kilonewton. Now you can calculate this value by using reactions we have calculated. So we have calculated this reaction, we have 52 kilonewton. Now if we will take at C, then we have directly 52 minus 50, that is due to this. So we are going to consider portion left of this, and automatically our value is 2 kilonewton. That is correct. And now we will go last, that is bending moment. We have to find out at C, which is 5 meters. And here we have again between simple supports, that is A and E, and we are going to get this triangle where we have this value as A into L minus A upon L. What is value of A in this? So A is 5. What is value of L minus A? That is 7.5. And in this way, we are going to find out this value 5 into 7.5 upon 12.5, that is equal to 3. And then we have to extend, that is whenever we have overhang. So you can see, so at this point, we have now similar triangles. So how now in this way, similar triangles we have to go in this fashion. Now we have this distance as 7.5. So we can have 3 upon 7.5, where we have to find out this value. So this value we have to find out, that is at point D, which is 5 meters. So that is into 5. And then we are going to get ordinate under 40 kilonewtons. And then this portion we have, that is again minus. In the same way, we have to find out, that is 3 upon 7.5. You can write over here into 2.5, and that is equal to 1. And then we have to go load into ordinate. If we have concentrated load, and load into area if we have UDL. So 10 into 1 half, 3 into 5, that is first portion. This portion we are going to consider between A to C, then plus 40 into 2 this portion, and this is again we have minus because in the same direction, and we are going to get value of MC, that is 135 kilonewton meter. Now we will have one problem, that is for cantilever also, and in this we are going to get ILD for array. Already we have seen that is 1 throughout, and if we will go for reaction, so we have 50 into 1, everywhere we have 1, so 50 into 1, and under this UDL we are going to get it as a rectangle, and we have this value of rectangle area, that is 3 into 1, and likewise we are going to get this value as 140 kilonewton. Now if we will go for shear force at C, then we know that we have these equations, and by using this equation we are going to plot, that is ILD for shear force. So you can see this. So already we have explained this, and we have this value, and then we are going to find out shear force. So we have this portion only, load into ordinate, and we are going to get shear force, that is equal to 90 kilonewton, 30 into 1 into 3, area under that load. And now we will go for bending moment. We know bending moment equation, we have MA into X. Then we will plot it. We have this will be 0 at A and maximum at B, that is 6. And then we are going to put the value ordinates at this. So first we have 3 over here, 1 over here. So we have 50 into 1, and then area under this plus 30 into 1 by 2, 3 plus 6 is this area. So load we have 30 kilonewton per meter, and this will be area of trapezoid, half 3 plus 6 into 3, and that will gives me value of bending moment as 165 kilonewton meter. So these are the problems we have considered, that is for influence line diagram, and in this way we can solve the problems which are related with our influence line diagram. So this will be about your ILD for simply supported frame. So today we will stop here only, and then we will go for second part, that is afterwards. So thank you.